Goed, goedemiddag, dames en heren. Welcome to our last seminar for the semester. Our speaker today is Trudie Sandrock, our colleague, and she's going to tell us about her experiences with first year data science. Thank you.
Thank you, Donnie, and thank you for coming on a Friday afternoon to listen to my musings about data science. I promise you there's no mathematical formulas in sight, so it shouldn't be too taxing. I actually want to start by quickly showing you something I recently discovered. This article appeared in the Journal of the American Statistical Association about 100 years ago, 99 to be exact. And it actually contains the text of the presidential address which the then president of the ASA, Robert Chaddock from Columbia University, read at their annual meeting in December of 1925, so really a long time ago. And this article, I think, sort of got lost or forgotten in the mists of time because according to Google Scholar, it's only been cited 7 times over the past 100 years. And as I said, I came across it completely by chance while I was looking for something else, but the title intrigued me because obviously I'm interested in undergraduate teaching of stats and data science. And according to the author, see there, he said that the function of statistics in undergraduate training not yet been clearly defined at the time, again, 100 years ago. And he said that at the time, there was too much emphasis being placed on technique rather than upon a mode of thought when statistics was taught. And he also said that the neglected aspects of statistical training meant that students began their careers without really understanding the field and without knowing what they are doing or why they are doing it. And according to him, this was in contrast to fields such as engineering or the natural sciences, where students, right from early on in their training, get a better sense of why they are doing what they're doing and also where they are headed. So when I read this, I got sort of an eerie sense of history repeating itself, because I think at the moment, we're not only at a time where once again, there's a lot of calls for reform in statistics curricula, but I think we're also at a point where the function of data science in undergraduate training has not yet been clearly defined. So my talk today is going to focus on this, and specifically in the context of teaching data science to undergraduates. I'm going to start by talking about the growth and popularity of statistics and data science, which really has been the driver of the need to train these data scientists. I'm going to talk about definition of data science. Yes, we're still talking about that. And also how it differs from statistics. I'm going to highlight some challenges in introductory statistics teaching that have been highlighted in the literature. And I broadly organize and summarize these in 6 themes. I'm going to touch upon some guidelines that have been suggested for the teaching of specifically introductory data science content, and also touch upon some pedagogical aspects that are important when we are looking at intro data science modules. I'm then going to go on by discussing some important considerations, which should be, in my opinion at least, taken into account when we are designing intro data science modules. And I'll specifically talk about my module, the module I developed, which is an example of a first year data science module. I'll show a bit of examples of learning material there as well. And then I'll conclude by highlighting some of the challenges I've experienced in teaching the module, but also talk a bit about how the content and the module itself is still continuously evolving. I think it was about 2008, Hal Varian, who at that time was the chief economist at Google, called statistics the sexy profession of the next 10 years. I know we've all heard the quote, we've probably used it extensively to plug our profession. But at that time, so 2008, there was already increasing interest in stats and also in the pedagogy of statistics. And I think that has really just increased since then, largely driven by all of this excitement and hype around data science. And this chart, compiled with data from Google Trends, with the search parameters indicated there on the right, shows that specifically over the past 10 years, this excitement around data science has really just exploded. Coincidentally, if you look at the graph there, it might seem as if it's decreasing a bit since a peak around the start of 2024. But if you actually go and look at the search term AI on Google Trends, you'll see that that really exploded over the past 2 years. So I think people are still searching for data science content. It's not that it's decreasing. I think they may be just wording it a little bit differently. Okay, so obviously this is not news for any of us, but the reason I'm showing you this chart is that this excitement around data science, I think, is naturally translating into an increasing demand for data science training. And obviously there's no shortage of short courses being plugged online or at private institutions where they promise to turn people into data scientists in sometimes a very limited number of hours, which I think is quite scary. And I have quite strong opinions about such promises, but that's not the purpose of the talk today. I think as we are increasingly talking about data science training, we should specifically be thinking about how we are equipping data scientists and training them at university or universities then. And this also comes coupled with the need to figure out how data science, or perhaps what the field of data science should entail, but also how it differs from the field of statistics and how it also differs from other closely related fields, such as mathematics and computer science, for instance. And that really is the purpose then of my talk today. First hurdle in all of this is that still, after all these years, there's still not broad consensus about what exactly data science is. And the term data science is used in different ways, both in industry and in academia. And the problem, of course, is if we don't know exactly what data science is, how do we know what we should be teaching when we are teaching data science? And here are just a few of the definitions I found in the literature, but the definitions of data science in an academic context specifically. And I won't read through all of them now, but actually, if you do read through these definitions and other ones as well, I always find it amusing because if you look at that last one, for instance, they call data science the science of learning from data, which if you look at the definition of statistics used by the American Statistical Association on their website, statistics is the science of learning from data. So I'm not sure why in some environments they still debate about the role of statistics in data science, if by its very definition, statistics stands core to data science. So I think it's no wonder that Rachel Schutt and Kathy O'Neill in their book, Doing Data Science, say that for statisticians, data science feels a bit like identity theft. And I think together with identity theft, perhaps data science has also caused a bit of an identity crisis in statistics because there is large overlap between statistics and data science. And this overlap really complicates the design of curriculums at a tertiary level because we have conflicting viewpoints about firstly the natural home of data science, where should we house data science in universities. And Helen McGillivray in a 2021 editorial actually said that there's this danger of departments all rushing because they want to own the academic space of data science. And already said that there's clear overlap, but actually the lines between them are also increasingly blurred, as Schwab and McCoy also write in their 2021 paper. And Brad Efron, who we all are aware of, in a plenary speech in 2019, he actually said that statistics has a strong positive regression coefficient with data science. So just further highlighting this overlap between stats and data science. And Gould in a 2021 paper said that finding meaning in data, which obviously is the domain of data science, sits very firmly within the boundaries of statistics. Okay, so clearly huge overlap between the fields, which means we need to determine how the two fields, if at all, how they are different pedagogically. And we need to ask ourselves, is there room for data science as a separate discipline? Or should we be teaching it as part of statistics modules? And also once we've fleshed that out, there's this need to disentangle the two, and so that we can then learn from the challenges that have been facing introductory statistics, causing this call for reforms in the curriculum over the past number of years. Now, before I get to a summary of these challenges that have been facing stats curricula, in 2010, there's this very well-known article by Deborah Nolan and Duncan Temple-Lang, where they call for the introduction of computing in statistics curriculums. And since then, there have been plenty of other studies also calling for the reform and modernization of the statistics curriculum. There are list just a few of them. And there have also been many other studies that specifically focus on the challenges facing statistics education. And these challenges have just been exacerbated by things like the explosion in available data, increased awareness around the power of data, and also then increased demand for data science capabilities. So in the literature, I've listed some of the studies, I'll list plenty more going forward. I think there are 6 broad themes, in my opinion at least, that arise in terms of the challenges that are facing intro stats curricula. And the first one, I think, is that the literature, at least the studies that have been conducted, feel that there's been too heavy methodological focus in statistics teaching, which then leads to students' inability to transfer knowledge. And there are just a few of the studies that have highlighted this. I think there are many different flavors of introductory statistics, but if you grab a handful of intro stats textbooks, it does seem that there's at least broad consensus about the type of topics that should be taught in introductory statistics. And in many universities, ours as well, the first year stats module is compulsory for many first year students so that they get a broad overview of the field, but are also exposed to important concepts such as statistics and such as uncertainty and variance. But even though there are these important concepts that are touched upon in intro stats modules, these topics are often more methods focused. And studies have shown that students actually have difficulty applying their knowledge, which they acquire in these modules, in new situations. Perhaps because, as Gerd Gigerenzer, who I also reference over there, he says that statistics tends to be taught as a set of rituals. So students are solving problems and doing analysis without understanding what they are doing or why they are doing it. In statistics, mastering key concepts is one thing, but that rarely translates to statistical reasoning for the average student. And I think perhaps the overarching argument here is not that the content of introductory stats is not important, but perhaps the way it is being taught in many modules slightly too focused on methods, which is problematic when we're trying to train modern statisticians, I think, especially in our field, stats and data science, where new developments are coming along so rapidly that curriculums really can't keep up. So we should be equipping our students to be lifelong learners if we want them to be able to keep up in such fast changing fields. And this is a difficult outcome to achieve if we are focusing very heavily on methods and techniques. A second challenge that has been identified is that in stats, again, often the content is presented in a very linear fashion, and that can lead to problems. Makar and Rubin specifically says that we should instead be teaching statistics as a process, not just as a set of artifacts and objects. And this is especially important since we now understand that learning itself is not a linear process, but a dynamic one. So I think progression in the curriculum should then not be teaching intro stats and computer science at the start and only getting to intro to data science in later years of study for students, which is unfortunately typically still the approach in many institutions. A third challenge is mathematical anxiety, and I think also negative attitudes about mathematics. If we include lots of mathematics in first year modules, it can actually be a deterrent for some students. Now, I'm definitely not saying that maths is not important. I think mathematical concepts is a core component of training for any statistician and data scientist. Otherwise, we are just churning out graduates who can apply techniques without really understanding why they are doing it or the mathematical underpinnings thereof. But perhaps focusing too heavily on math in first year studies runs the risk of alienating some students. Fourthly, insufficient focus on context. And the study by Wild and Fanku, which I reference over there, they lament the fact that, and I'll read what they said that the arid context-free landscape on which so many examples used in statistics teaching are built ensures that large numbers of students never even see, let alone engage in statistical thinking. And this was written 25 years ago, but unfortunately, I don't think that much has changed in that regard. Helen McGillivray, once again, in a 2021 editorial, said that it's clear that traditional introductory statistics education has been lacking in that regard, even though statistics is probably the most context dependent of all the sciences, according to her. And Cobb and Moore, also in a study I referenced over there, said that mathematics and statistics are different in the sense that statistics requires a different kind of thinking because, and according to them, data are not just numbers, they are numbers with a context. So it seems obvious that context should not be ignored when we're working with data, but sadly, I think in many curricula, it is still the case in introductory courses. A fifth challenge that I think goes along with this in some way is that statistics training often is still limited to small, very clean data sets, instead of emphasizing the solving of real world problems. And by focusing on such small data sets or toy examples exclusively, students run the risk of seeing statistics perhaps as old-fashioned or something that's only useful for small samples in a very carefully controlled experiment, which we know is not the case. And then the last challenge, not enough coding at introductory level. I've already referenced this article by Nolan and Temple Lang, where they called for a bigger emphasis on computing in the statistics curriculum, but there have been many other studies that have also emphasized this. And I think especially since many statistics students don't take any intro computer science courses, and for many students then their only exposure to coding is in a statistics course. Unfortunately, often this is left until later modules, so advanced undergraduate or even postgraduate level, which runs the risk of students by the time they graduate not really having sufficient depth of programming knowledge. And there is actually sufficient evidence, if you go and look at the literature, that the inclusion of coding and such technological capabilities at an early level is very beneficial. For our students. It can help them to discover a passion for statistics or data science. And there's also evidence that stealth learning of programming skills can be beneficial, and that stats or intro, specifically an intro stats or data science classroom can be the ideal place to introduce coding to students. And integrating coding throughout a course or a program can actually also help to increase student engagement. All right, so if you look at these 6 broad challenges facing introductory statistics curriculums, I think the temptation can be there to rush in to make large-scale changes to the existing modules. And I think there have been, fortunately, there have been cases where the statistics curriculum has been modernized, and some or all of these challenges have been addressed. But I worry that in doing so, unfortunately, what ends up being sacrificed is exactly the type of content that teaches our students statistical or inferential thinking, which obviously is something that they need to be well versed in if they are going to be practicing as statisticians or data scientists one day. And I've already mentioned this speech by Brad Efron, where he said statistics has a strong positive regression coefficient with data science, but he actually followed that with a phrase, as long as we remember not to let the inferential side of statistical thinking get lost in the excitement over new technology. And I think this last bit is crucial, but unfortunately it is something which sometimes tends to get overlooked, especially in intro modules. And Gould, in a 2021 article, also emphasized the importance of statistical thinking. And he said that there's the concern that in the excitement to develop more data science curricula to meet the growing demand for a data literate citizenry, new curricula will overlook or neglect the foundational field of statistics. So I am therefore of the very strong opinion that unless we are talking about a service course, we should be teaching data science ideally as a standalone module. Instead of trying to incorporate data science content or modernize the statistics curriculum, the stats curriculum, right, is already, it's fairly full, the content of our intro stats, our stats module. So something has got to give if you want to include more content. And in some cases that I've encountered in the literature, what ends up having to give or being sacrificed then is exactly the inferential type of content or the mathematical content that is still important for our students to be exposed to at some point during their intro training. So if we develop data science modules, ideally we should do it as standalone modules so that we can introduce some modern content, obviously alongside the inclusion of coding, but also still teaching some important basic stats principles. Obviously, if we're saying we should be teaching data science to intro or as an intro level module and also as a separate module, that's one thing, but what then should go in that module content-wise? Unfortunately, there have been quite a few guidelines in the literature in this regard. There I list just a few of them. So there's a 2017 report by the Park City Math Institute. There's also a report by the National Academy of Sciences, Engineering and Medicine, and another 2021 report by the Association for Computing Machinery. And there's also several articles or papers that have described specific individual courses that have been developed in terms of intro data science. Unfortunately, I think many of those are very US focused, the guidelines and the papers that have appeared, which means that it isn't necessarily applicable to tertiary institutions in other countries, because obviously school contexts and curriculums change or they differ from country to country. Sometimes they even differ within countries. And students also differ in institutions based on what subjects they can take alongside stats and data science. So it also means that students come into such courses with different backgrounds. Nevertheless, I think there are some broad themes that you can identify from all of those in terms of the content that should be included at an intro data science level. And these are programming, coding, machine learning, data wrangling, data visualization, and data communication. Next step now, if we have some broad idea of the content that should go in a data science module though, is that actually there has been very little research, not a lot published in terms of the pedagogical aspects of data science curriculums. And actually there's this paper written in 2021 by Fries and co-authors where they say that there's a wide gap between educational research and the design of curricula in statistics. Yes, they're talking about statistics, but I don't think that it is any different in terms of data science. Another article by Sanchez Pina et al. From 2023, they say that in data science, not much attention has been paid to supporting the cognitive processes involved in learning data science concepts. This is something that was echoed in a study last year by Mamarian and Doleg, and Theobald and co-authors in 2024 said that the effective teaching of data science does not stop at developing a novel curriculum, which is what most of the literature up to now has addressed, but requires an understanding of student perspectives and how they make sense of information in the process of learning. So there really is a lot of scope for social research in this regard for anyone interested in that. In this landscape of very little research on the pedagogy of data science, I think there are some important theoretical and pedagogical frameworks that we should be taking note of, and I'll just briefly highlight some of them. First is this concept of adaptive expertise rather than routine expertise. Now, statistics and data science both are, I think, rather complex domains for students to master. It requires students to accomplish more than just mastering skills, but it also requires them to reason with abstract concepts and data and ideas. And the study I referred to on the previous slide by Fries and co-authors, they actually said that students in statistics are often able to master small bits of knowledge without truly understanding the domain in a deep way. Obviously, this limits their understanding of the underlying structure of a domain. Okay, so that also means that students struggle to apply what they've learned to new concepts or new scenarios. And I've already mentioned that this is something that is important in fast-changing fields such as ours. And this is then what Hatano and Inagaki refer to as adaptive expertise, which is the ability to apply existing knowledge to unseen or novel situations, which is in contrast to what they term routine expertise. Now, to acquire adaptive expertise, or if we want to equip our students with adaptive expertise, we can't simply expect to provide them with information which they passively receive in a lecture, or just give them a list of things to memorize, or expect them to automatically understand or apply techniques. But instead, we should be giving them opportunities to construct their own knowledge. And this then falls under the learning theory of constructivism, which hails back to research, I think, conducted in about the 1960s, but actually is described, or a very nice overview is given in this reference over there by Narayan. If we expect our students to be able to integrate the existing knowledge, this is now from the Narayan article, and develop a more mature understanding of a subject, we need to lead them into a deeper understanding of the subject matter. So it's not something that is just passively transmitted to them in a lecture. It requires a bit more than that. And it's also not something that's going to happen overnight or in a linear fashion. And in this regard, I think the constructivist theory of what is termed a cognitive apprenticeship is relevant. Now, in a traditional apprenticeship, we have a trainee who is guided through his learning by an expert. Sometimes the trainee will learn by watching an expert perform a task, or sometimes the trainee will perform the task himself, but under strict guidance of an expert. And importantly, this also happens in a real world context, not in an isolated classroom somewhere. So in this regard, the concept of a cognitive apprenticeship was defined by Collins in 1989. And there's also a very good book chapter by Denner and Berner that describe this cognitive apprenticeship model. And they define it as learning through guided experience and expert demonstration. And in this model of learning, students are challenged with tasks that are maybe a little bit more difficult than they would be able to accomplish on their own, but they get the opportunity to practice performing this task, but under supervision and with expert guidance. And the advantage of this, in contrast again with the traditional lecture-based approach, is that students, yes, they get the opportunity to observe an expert perform a task, but they're also learning within context, which is very important. We've already established that. Fennell et al., just as an aside, take this a step further, and they define what they call the computational apprenticeship, which has the aim to develop computational adaptive expertise among students. Now, the apprenticeship model is obviously useful, and students can learn by doing, and specifically by doing something in context. But the important thing in an apprenticeship model is that there should be guidance by an expert. And in a university classroom setup, it's not possible for us to give one-on-one individual guidance to students. So instead, this is accomplished through a process known as scaffolding, which was defined by Wood in 1976, where students get guidelines, step-by-step guidelines to take them through a task. And this was specifically also addressed in a data science context in that article by Sanchez Pina. And I've referenced this article previously as well. One very last pedagogical aspect I think we should take note of is that of the spiral curriculum, which was introduced by Brunner in a book in 1960, and basically is an educational approach in which students are repeatedly revisiting key concepts throughout their education, but each time they encounter the concept again, it's at a slightly more advanced level. And in this way, a curriculum can deepen students' understanding and also increase their grasp of the structure of a field. And this article by Quinn et al. That appeared very recently, they actually discuss a spiral curriculum in a machine learning context. All right, so confession time though, even though I've now listed lots of challenges facing stats curricula and also lots of pedagogical and learning theories, I have to confess that I didn't really figure out how my module slotted into all of that until after the fact. When I started out developing my module, I just had this very vague idea that I wanted to introduce coding from the very start because I wanted students to learn by doing. And then one sort of pet peeve of mine, a problem I've always had with statistics training, is that I feel we introduce the big ideas in statistics at a very late stage in training, which is in contrast to fields such as laboratory sciences or economics, for instance, where students get exposed to the big ideas in the field right from the start. And I think if we delay this, we might firstly lose some students who perhaps have the potential to be great statisticians or data scientists, or who might derive great joy from practicing statistics and data science, but they never get to see what the field is about when they are testing null hypotheses in their first year compulsory service course. So then they're lost to the field forever. And secondly, I also think that it helps students to understand where they're going. So if we introduce them to the big ideas in the field right from the start, it helps them figure out how all the other things they need to learn, such as linear algebra and statistical inference, how that slots into the bigger picture. So I set out with this idea that I want to introduce coding from the start, and ideally I wanted to expose the students to advanced statistical learning concepts right from the beginning. There were then some important aims for the development of such a module. Again, post hoc, it might sound like this was a very well thought out process, but it wasn't. Always easier to go back afterwards and put everything in context. But nevertheless, the first aim is that I wanted to develop students' statistical thinking and reasoning. I already earlier said why that's important. And Garfield and Benz V define statistical thinking as knowing how and why to use a particular method or model, and also a deep understanding of theories and their limitations. Ellen McGillivray again, but this time in a 2022 editorial, said that foundational learning requires sufficient learning of statistical thinking. Now, the obvious question is, how do we teach statistical thinking? And one way of doing this, according to Dierke et al. And also Van Koog et al., they echoed that in a separate article, said that we can teach statistical learning by learning to model, because by learning to model, students gain a deeper comprehension of statistical thinking. And in a different article, in a different approach, this time by Gould again, he said that data visualization can actually also be used to teach statistical thinking, because in order to be able to interpret a data visualization, you need to understand concepts such as variance and distribution. So that meant for me that at least data visualization and some form of predictive modeling had to be included in my module. Secondly, I wanted the module to encourage students in terms of multivariate thinking. Again, the literature, this is from a study by Horton, the first one over there, says that a lack of appreciation for some simple multivariate methods is a major limitation, because that means students don't see the potential of statistics early in their training. Seton, Kaya, Rundle, and Ellison also emphasize the importance of exposing students to models with many variables at an early level already. I think this is in contrast to the typical approach where in intro courses we tend to stick to univariate statistics. And this is even though Wageman in a 2016 paper already described the course, the entry-level course, in which she showed that it was possible to successfully teach multivariate methods to students at this very early level. Dierke again, and once again, McGillivray also argued that foundational thinking should not be constrained to just one or two variables. So that was a second aim for me, exposing students to multivariate nature of statistics and data science. Next aim was that I think a critical skill is that students need to understand that working with data is a cyclical process, The importance of this has been highlighted in many studies, and also the advantages thereof. Harding and a few others as well have shown that if we are teaching data science and statistics within this context of the data lifecycle, it's a way of fostering statistical thinking, once again, in a meaningful way. It also, I think, moves away from this idea that students sometimes have that there's a single correct answer to a statistical question. And according to Hicks and Irizarry, it also puts the problem first instead of focusing on methods first. And then a study by Fankook et al., where they said that it also teaches students to shift between the data and the models that are constructed from the data, and also the context in which all of this happens. And then the last aim, for me at least, I think the most important one was that I wanted to expose students to the big ideas first. And I've already said that this is in contrast in statistics and data science often to what happens in other fields where students are exposed to the big ideas early on. There's actually this great little mathematics, I don't know if it's a textbook, but this book by Russell and Corwin, where they talk about teaching mathematics to primary school kids. And there they say that great literature, we don't keep those away from students until we think they are capable of appreciating or understanding it. We encourage students to read great literature, even when they're young, so that they can appreciate the field and also learn from it. And yes, I suppose we could argue that stats and data science are complex fields, but actually in their book, Russell and Corwin show that it's possible to expose students to big ideas in mathematics in primary school already, and that an easy way of doing this is by working with real world data, and that it actually works really well. There have been a number of studies highlighting the importance of identifying and teaching big ideas early on in students' careers, and there I list a few of them. Obviously, we need to answer the question, what are the big ideas in data science and statistics? There are some studies where they address this on a more conceptual or broader level. There have also been some studies where they looked at this specifically in terms of data science. Setinkaya, Rindle, and Ellison, they have this approach which they call let them eat cake first. They accomplish this by, in their curriculum at least, by incorporating interesting data sets. And they, for instance, they teach the mean as a model, type of empty model, and then they progress from there up to a general linear model. But they also focus very heavily on data visualization. Wang et al. Also says we need to be bringing big ideas into interest stats early and often. Again, they limit that to data visualization in their course. Okay, so my opinion then was that statistical learning theory is a big or core idea in statistics, in data science, specifically for the module I was developing, and I wanted the students to expose to that from the start. I'm not alone in that opinion. This is, again, the same article that I've referenced several times now by Fries. And they say if we want students' knowledge of introductory statistics to transfer to advanced courses, we should connect what they are learning to the concept of modeling from the very beginning. Yes, they again are talking in the context of statistics, but I think this applies in terms of data science as well. There are several other authors who have also said that we need to establish data skills, including modeling, in introductory courses as it exposes students to inferential thinking. Should just highlight, and that's why it's in capital letters, that this idea then of incorporating statistical learning models in an introductory course is not a novel idea of mine. There have been several studies where they have called for that. I've already mentioned the study by Sun et al. They also specifically include general linear models in their intro course. Two other studies, Setinkaya, Rindle, and Ellison and Gierke, they specifically teach regression at an introductory level, and a different course by Loy et al. They include trees as part of an intro data science module. All right, so definitely other suggestions have been made in the literature for including predictive modeling in an introductory course, but most cases I've encountered, this is limited to mostly one type of model. So either regression A lot of the times it's regression, sometimes trees, but typically it's not a wide array of statistical algorithms that are included in the intro courses. And in my opinion at least, I thought it was important for students from the word go to step away from this idea that there's, I've already said this as well, that there's a single correct answer. And I wanted them to see that there can be more than one way of answering a statistical question. So for instance, having one data set, but being able to apply different classification models to the data set. So I wanted to expose them to a wide array of models from the word go. Also, perhaps I think because I wanted to avoid a Maslow's hammer approach, you know, if all you have is a hammer, everything looks like a nail. Sometimes I've seen that in the past, especially with my third year students who, because they are very familiar with regression and know it really well and have mostly encountered regression models, they get a data set, they just want to apply regression to it without thinking about anything else. So I wanted to hopefully avoid that happening in these students. So finally then, to the module that I developed, which was called Data Science 141. It's a first year, second semester module. By the time students get around to this module, they've already completed an intro course in probability theory and statistics. So they have been exposed to basic probability concepts, including conditional probability, concepts such as random variables, expected value, variance, and they also know some basic discrete and continuous distributions. They've also, by the time they get to Data Science 141, completed an introductory computer science module. And in the module, we have students from many different programs. We have students from the 4-year BDATSI degree. We have students from the engineering faculty who are doing a focus in data engineering, and also BSc students who are doing the focal area data science within the BSc computer science degree. Soon, the module will also include BCom mathematical sciences students who are following the focal area data science, and there will be more programs added to the module as well. Our structure at this stage for the module is 6 hours a week of contact time. 2 of these are in ordinary lecture venues where we cover theoretical concepts, and then 4 in electronic classrooms where we do more practical work. And this is the 6th year that the module will be presented. It was first taught in 2020. Actually, after having developed the module, the COVID lockdowns hit, and it was a mad scramble to adapt the content to make it suitable for remote teaching. That's a different story for a different day. The core content I cover in the module, I list over there. It's not necessarily presented in that order. We'll switch it around sometimes. Also, we'll often encounter a topic very informally and briefly, and then revisit it at a later stage in the module in a more formal way. Actually, before we get to any of that, we start with a bang, and I introduce students in the very first week. I introduce them to R and the R Studio software environment. Again, I think talking about why R, I think, is suitable for use in an introductory level is also a topic for another day, but there has been quite a few studies that have shown that especially the tidyverse approach in R is beneficial for students, especially for entry-level students. Sun et al. refer to R as having a germane load, meaning it doesn't increase the cognitive burden for students, but instead lightens it. Things such as the natural language verbs that are used in dplyr, the consistent syntax across all of the functions in ggplot2, and also the use of the tilde notation for models in R actually makes it easier for students to focus on the outcomes they want to achieve and not get bogged down in trying to code things from scratch. And actually, Gierke et al. Have shown that this tilde notation that is used consistently across R for models has the additional benefit of fostering model thinking. About a quarter of the way into the module, we also introduced the students to R Markdown, not only to teach them about the importance of reproducibility of research, but also to restore that connection for them, at least in their minds, between data, coding, models, and also communication of results. So the typical approach we take is that We start with, for each topic, we'll have 1 or 2 theory lectures where I cover the basic concepts. For this, we'll often use small or toy data sets, simply for the fact that to illustrate theoretical concepts, we can then visualize the data and we can also perform manual calculations. But then after this very brief intro to the basics, we will then work with real world data in our practicals where we implement the models in R. We'll use larger data sets in this regard. And then in class, we also have discussions about the interpretation of the results. We also have tutorials after the practicals then, where students will be given a different data set, still a real world data set, and usually a fairly large one. And they then get a set of questions to guide them through the analysis. So they're not left on their own. They have these sort of guided, open-ended questions though, to help them foster their statistical thinking. And we also have teaching assistants available to help during the tutorials for students who require more individual assistance. But I also allow students to do the tutorials on their own, in their own time, and I provide them with model solutions afterwards. This is just an example of some of the learning material I use. And perhaps before I show you that, the question, I'll go back another slide actually. If you look at the content over there, I've now spent quite a bit of time talking about why I at least thought that it's important to introduce students to statistical learning concepts early on. But it's one thing to say that it's important and to make an argument for it. But the question is it actually practically possible to teach statistical learning concepts to first-year students? And I think in my experience, it turns out that yes, it is actually possible. Because I think many of the concepts at their heart is not that hard to understand. Something like a decision tree. Yes, a first-year student doesn't have the mathematical sophistication to understand an advanced algorithm. Something like entropy is mathematically not that hard to explain to a first-year student. And once you can calculate entropy, you can calculate information gain. And if you understand information gain, you can think about how you can recursively partition data so as to maximize information gain. So it's actually a very natural process. And by the end of it, students can fit a decision tree. Yes, not an advanced one, but a rudimentary useful model. K-nearest neighbors, I think, also is something which mathematically and conceptually is not hard to understand, even though in my own studies, I only was exposed to that at a postgrad level. My 16-year-old daughter did a term going to school in Germany last year, and there they actually, as part of the informatics subject, they taught the K-nearest neighbor algorithm to a class of 16-year-old students. So it is possible to explain it at a fairly basic level, because again, Euclidean distance, mathematically, it's not that hard to understand. And once you can calculate distance between observations, you can think about how these distances and the idea of neighbors can be used to help classify new observations. And actually, even in practical, you play around then with different values of K, that very naturally leads into discussion about things such as overfitting. So at this very basic level, we cover decision trees for classification, naive Bayes classifiers, K-nearest neighbors, linear regression models, and then also cluster analysis. We look at both hierarchical clustering and K-means. So we cover both supervised and unsupervised learning in the module. And this is then an example of the learning material specifically for decision trees. Actually, even before we get to the entropy calculations, you see there, the textbook has a very nice, simple, intuitive example where they have little stick figures with different colors and shapes for their heads and their bodies. And it introduces this idea of recursively partitioning subsets until you get purer subsets. So then we can talk about how we evaluate the purity or impurity of a set. So that brings us to entropy. So there is one very simple, again, this is now the toy kind of data set we use for the theory component. We can show how we can calculate the entropy in a set and also the subsets after splitting is taking place. This figure is actually from the textbook. I just included the entropy calculations on there for the students. Once we've done that, we can now take a different variable, same data set, but different variable. We calculate entropy for those splits. And now, even before we get to information gain, we can very intuitively look at these two splits and discuss in class which one actually do we think gives us a better segmentation of the data. And that then leads us into a discussion of information gain, show them how to calculate information gain. And once you can do that, we can construct a very basic tree, such as the one over there. We then, in our practical, we use a large data set. Specifically for the trees topic, we use perhaps not that large, but 20,000 observations from the mobile phone domain. Specifically, the aim is to identify customers or to predict instead customer churn. And students are guided throughout this process. And if I say guided, I don't mean just give them a few lines of code that they have to type in, but through the whole process. So from getting the data, exploring the data, talking about variable types and model types and so on. We guide them through fitting a tree such as that one. And we also don't stop once the model has been fit. I mean, obviously we've got a tree model. We can talk about evaluating the model. We can talk about using the model to make new predictions. But we also then chat about, for instance, in this model or in this tree, we see that not all of the variables were used. So that naturally leads to a discussion about something such as pruning. And then we use a different data set in our tutorials. All right, so very briefly, I'm almost done. Question is, does it work? Now, obviously with this kind of thing, it's hard to conduct a controlled experiment to see whether it works, but I think there is anecdotal evidence that it is working. We've seen big growth in student numbers, also students switching to the data science program once they see the early stage what data science is about. And in terms of student feedback, it's generally positive. And students say that they actually value getting this early exposure to what the field is about, and it helps them better understand once they get to more advanced math or statistics modules to see how everything fits together. And I think it also gives them a sense of accomplishment because they can now, even in the first year, they can take a data set, fit a model and use it to make predictions. I'm not sure they necessarily get the same sense of accomplishment from testing an hypothesis in first year stats. So the feedback from students has been generally positive. And this then echoes what Bird Al says, where we should equip our students to become capable of obtaining serious insights and accomplishing powerful results early, because that supports their motivation and willingness to believe in their own learning capabilities. Please note, I'm not advocating this as a one-size-fits-all approach. I don't think it will work for all modules. I teach first-year probability theory. I don't think such an approach would work for the content over there. But I think an intro data science module is an ideal place to introduce students to more complex topics and also to include coding from the word go. There have been challenges. Student numbers have been growing. Started with 45, we were up to 250 last year, projected to grow even a lot more. So obviously it makes it difficult to keep the class interactive. Also makes assessing the content challenging. I'm currently using written assessments to test insight, but take-home assessment to test the R skills, because I feel for beginners, a timed coding assessment is unnecessarily stressful and also doesn't really mimic a real-life coding environment. Also find that students have diverse computing backgrounds. So some students, lots of exposure to coding, and they get bored if they watch me demonstrate something in class, while other students need a lot of assistance, even tech support. So to address this, I've been setting the practicals as hybrid so that students with strong skills can do it on their own. And we can spend more time in class talking about the interpretation of results. And the module really is continuously evolving. So for instance, this year, I want to try a bit more of a flipped classroom approach, both for the practicals and the theory lectures, because I think some of the basic concepts can be easily explained in detailed notes through videos, and I want to use more of the class time to chat about case studies and interesting applications of data science, so that students also get a chance to practice those communication skills around the applications. So in conclusion, I do strongly advocate introducing statistical learning theory in introductory data science courses for all of the reasons I mentioned here today, but perhaps also to illustrate to students the relevance of what we are teaching them. I can promise you that no one in this course has asked me, when will I ever use this? So I think it is important that we show our students what is possible we need to give them the opportunity to get their feet wet at an early level. And continuing with the water metaphor, Hadley Wickham wrote in a commentary in 2015 that we must give stats students the skills to dive into the data ocean. Yes, there are sharks and jellyfish and riptides, but we cannot be paralyzed by all the potential dangers. Students will go swimming with or without us, and all we can do is prepare them as best we are able. All right, so I have very long list of references. It was too much to put on a single slide. It's about 5 pages, so please email me if you would like me to share any of the references with you. I would be happy to do so. And that is it.
From back to this side, you have is a personally concepts. You start covering a wide range of concepts. How do you manage that? And I think you should, because the intro, there's presumably the rest of it you build on.
Yes, so that's that whole idea of a spiral curriculum. So I think we spiral within the module. So I'll perhaps introduce something like overfitting very informally when we start by fitting trees. And then towards the end of the module, when they have a bit more exposure, we'll introduce overfitting more formally. We'll play around with data and see what happens when we overfit. But then all of the models we cover in this module, they actually get exposed to that again in their second and third year modules as well. So we spiral within the module, but also across years. So they'll do something such as k-nearest neighbors again in their second year and their third year of study, but at a more advanced or complicated level. So that helps to lead them, hopefully, into a deeper understanding rather than the rudimentary basics we can teach them at a first year level.
Question. I could probably spend hours asking you a question, but just a basic one. You're such an introductory stuff, just for my clarity, you're not talking about terminating.
No, that's why I said I'm definitely, I think that has been the approach that some institutions have taken, because there's all of this new content that I think is important for students to be exposed to, but then they plug that into either they replace intro stats courses or they try and incorporate it in stats, and then we throw out the content that I think is very important, the basic math and the inferential content that we still need students to be exposed to. So I'm definitely advocating that these types of content should be taught as a standalone module alongside our standard introductory stats courses. So we haven't terminated anything. This is just an extra module which students are now taking.
It's also very different to your stats and data science versus your standalone.
So stats and data science, that's completely standalone, because those students, they don't get to take this module as well. But students who take this module, for instance, they have all taken computer science 113 or 114, and also probability theory and statistics, either 114 or 144, and maths 1.
Much more mathematically.
Yes. Yes.
So just one question for me, given all the overlap you mentioned and definitions, what would your personal definition be of data science as opposed to statistics? So I asked that because you do teach the probability theory and statistics, and then this is different. So how in your mind are they different? I'm just interested in your experience.
Yeah, I think if you ask different people, you'll get different opinions. I think data science is context, more domain driven. So we work with real world data within context of the data. Don't just work with small human data sets like 188 at least. We have small human data sets. Now we do 30 data sets, big data sets. We wrangle the data, we visualize it, but all within context. So I think that's one core difference. Yeah. Yes. I think fortunately, because I also teach the first year statistics module. I teach the second semester version, but I know the content's exactly the same as what they do in the first semester. So I know exactly what they should know from there. So for instance, when we do need-based classifiers, talk a lot about conditional probability. So we'll go and revisit some of the stats concepts that they were taught in that module and show how we can now use this idea of conditional probabilities and independence to help us on fitting need-based classifiers. So we constantly referencing between them.